Okay, now we assume the prior is a beta distribution with parameters 2 and 2, and we have to write down the posterior, compute the MAP estimate of theta. So first, let's import our likelihood, right? We're gonna need this one. So sorry, I'm lazy. I can copy it, but I'm lazy. And then what do we need? Bayes rule. Okay, so let's first define a beta distribution and its PDF and its formula. So if X, let's say, a random variable, follows a beta distribution with parameters alpha and beta, then P of X is equal to a K, let's call K now here, a normalizing constant to make sure the PDF integrates to 1, whereas we won't have a valid probability distribution, right? And sorry, X to the power, I believe, alpha minus 1, yes? 1 minus X to the power beta minus 1. Okay, this is what the beta distribution looks like. And a reminder from Bayes, Bayes rule, seen it many times. We can, like I said before, omit this guy and use a proportionality symbol that kind of looks like this, like a fish, whatever. So the probability, the posterior proportionality sign, which also looks like an alpha. Please don't, because I read them pretty similar, so don't get confused. This is a proportionality sign here. Is proportional to the likelihood times the prior. Yep. So what do we have here? We have theta follows a beta 2 distribution. So what do we know? We already have, so we're trying to find the posterior, right? The posterior is this guy. And we already know this guy, the likelihood, it's this. We want to find this guy, the prior. And there we are given that the prior follows a beta distribution with parameters 2 and 2. So this is enough, given what we just defined here about beta distributions, to know that the prior looks like this. Some constant k22 times theta to the power alpha minus 1, 2 minus 1 is 1, times 1 minus theta, 2 minus 1 is also 1. And that's great, right? Because now we can write the posterior is equal to, well, is proportional to, I should say, these guys, right? You already wrote this here. So let's move stuff around now. Everyone agrees with this, right? So we had this formula, we took this, and we took this, and we just put them in their places, right? So this is great. There are a few terms we can simplify and group together, right? And we can group these guys together. So let's start by grouping these guys together into another constant that we will name K prime, let's say. So this implies the posterior is proportional up to a constant to something called K prime, right? It's this and this. And then the rest becomes this, right? So you can see, this kind of looks like this guy over here, right? So this hints that the posterior follows a beta distribution, right? In fact, the posterior follows a beta distribution with parameters alpha equal to 9 and beta equals to 5, right? Because if this is beta minus 1, then 5 minus 1 is 4. And if this is alpha minus 1, then alpha minus 1 is 9 minus 1 is 8, right? Okay, great. Now we have the posterior, and then we want to maximize it, right? To find the maximum a posteriori parameter estimate. So theta hat MAP, again, we use the hat to talk about estimates of parameters. This is equal to argmax over theta of the posterior, right? Which is proportional to argmax of theta. And here, since this constant, normalizing constant, doesn't depend on theta, we can omit it from the maximization, right? So we only need these guys. Theta to the power 8 times 1 minus theta to the power 4. And if we want to maximize this guy, we're going to do the same steps. Differentiate, take the log, actually, because computational convenience. Take the log, differentiate, set to 0, solve. So maybe we do like a roadmap here. Differentiate. No, sorry. Take the log, then differentiate, then set to 0, then solve. It's our little roadmap. So let's start with the first thing in the roadmap. Log theta, log of the posterior is equal to log of this guy. Okay, let's write it. I'm not gonna skip some steps. And this is equal to, actually I am, because by now you know. Right, this is the log posterior. Let's differentiate this guy. So d log p theta given data over d theta. This is a partial derivative. Sorry if my handwriting is not clear. What is this equal to? 8 over theta minus 4 over 1 minus theta. Set equal to 0. And this says right, which implies this, which implies this, which implies in turn this. And then finally, theta hat MAP is equal to 12 over 8 over 12, which is 2/3, right? So you can see what we did here. We defined the beta distribution. We had the likelihood from the question previously. We used this relationship from Bayes' rule, the proportionality one. We computed the prior given the information that they gave us. And then we have the prior, the likelihood, we put it in to get the posterior. Then the posterior, we wanted to maximize it. How did this look like? Our roadmap here, our steps. You take the log, you differentiate, you solve to 0, and you set to 0, and then you solve, you get this guy.